Hello everyone, today we are going to talk about the Dijkstra algorithm, an algorithm that finds the best path between a source vertex and the other vertices in the graph. This is a path-finding algorithm that finds the shortest path. It computes the path of minimum cost from S to the destiny T. We are going to study this algorithm using directed graphs, and this works with graphs with cycles and positive weights. Let's talk about some details of this algorithm. Starting from the vertex S, it computes the distance, the dist SV, for all vertices in the graph. This keeps for each vertex V a value dist V in a dictionary that is an upper bound of this distance. This uses two sets of vertices, a set called fix that stores the visited vertices. If a node is in fix, there is a path of distance dist V stored in this dictionary. The second set is a set called eligible that contains the vertices that are not processed yet. This algorithm processes the vertices and edges once. During this algorithm, what we are going to do is to update this upper bound. So we have here a path already between S and B with cost 10. We can improve this path after visiting U. In this case, the distance to B is larger than the distance to U plus visiting the weight from U to B. In this case, we can follow this path here that will have a cost of 5. So again, this structure will store an upper bound of this distance, and new edges will update that bound. Let's take a look at this algorithm. Here we have the dist structure, a dictionary. This is the other dictionary that we are going to use to store the predecessors in order to recover the path. The fixed set here and the eligible set that is now including the source vertex. While we have nodes to process, we extract the node that has the minimum distance from the source vertex. We remove this from the eligible set, we include it in the fixed set, and we iterate over the adjacents of this node. If this vertex is not visited, we can here initialize the distance if this is a new node, or we can update the distance if we have found a better path to this node. Let's see an example in this directed graph. We can start from A. We include A in the eligible set. Now the closest distance is A with a distance of 0, so we can fix A. From A we can get to B and D. We can include them in the eligible set, and we can update the dist structure. Now we have a path to D with cost 5 and a path to B with cost 10, both starting from A. As we are selecting the closest path, we are selecting the path to D. So we are fixing now D, and from D we can go to E. We include E here in the eligible list. Now after including E, we can update the distances. Now, as we have fixed, we are fixing D, we can go to B through D with a better distance, with a better cost. In this case, 8 a cost of 8, where we had a cost of 10 going directly to B. In this case, we are marking here that we are going through D. Now we have to pick the closest path. D is already in fixed, A as well, so we can select the node E. We fixed E, and after fixing E, we can update the distance to C. Now we can go from A to D, and then to E, and finally to C, with a cost of 15 instead of 14 going through D and C directly. We have D fixed, we have E fixed and A, so between B and C we pick B and we mark B as fixed. Including B allows us to update the distance again for C. In this case, we can go from A to D with 5, from D to B with 3, and from B to C with 1, with a total cost of 9. That is better than the 15 that we had before. Now we have A fixed, B fixed, D fixed, and E fixed, so the only pending node is C. We can include C, and we have here the final dist dictionary that will contain the distances, the minimum distances from A to each to the other nodes. If we remove the edges that we are not considered here, we end up with this tree structure that contains the best path to each node. For example, from A to D, from A to B with a cost of 8, from A to C going through AD and B with a total cost of 9, and finally the path to E through D with a cost of 7. Thanks for watching, and see you in the next video.